All right, boys and girls, welcome back to the drive-through. Another spectacular Monday rendition sponsored by the deli. Oh, it is Tuesday. Nice. That's huge. It's gonna be a strange week. Like, we're gonna get teased tomorrow. We won't have any delay, but we will be here during a decent snowstorm. And then Friday's up for grabs. We might have a delay Friday, we might have nothing. We could be off. We could get stuck here. Hey, as long as we're stuck in Fourth Bell, I'm just fine. Alright, so, this is surface area and double integrals. Now, like it says, we are only going to be able to find the surface area of, like, the domes or the roofs or the ceilings of our solids. So this isn't a total surface area. What we can't find yet is the lateral area, but we're able to do that, I think, in section 14.2. So here we are today in, 13.5, okay? So, first of all, does anyone need to take their quiz? We're all good? We all took it? Okay. So let's think about what we're able to find. It is, I think so. We can find the area of that region with a double integral now, right? We could find it with a single integral before this class even started, but now we can find it with a double integral. Do you agree? If we treat this region like a planar lamina with a uniform density of 1, we could also find the volume of that region, and then therefore we could also find the center of mass and the moment of inertia, right? Okay, if we've got a function over the top of this thing, we can find the volume of that thing now. Right? Right? Yes. Yes. Double integral, the volume of that solid, that silo-looking thing right there. We could find the volume of it by taking a double integral with a z equals function on the inside, and that z would represent the height. So we do know how to do that, okay? What we're doing today is we are finding the surface area of this cap. Does that make sense? We're finding the area of that cap. It's not a lamina, so the area of the inside is the same as the area of the outside. If that thing had thickness, then the area of the outside would have a bigger surface area than the area of the inside. Do you agree? Thank you. Appreciate it. All right, so now let me tell you where we're going. In 13.6, we're going to give this whole solid a variable density, and so we're now going to be able to find the volume if it has a variable density of this solid. And then if we could do that, then we can find the center of mass of that solid, which we can't do yet. And we could find the moment of inertia for that solid. So that's where we're going. And then in chapter 14, we will finally be able to find the lateral area, and so we'll kind of have our geometric completion certificate at that point. Yes?
Right now, is it hollow?
Right now, is it hollow? Well, yeah, right now it is hollow. Yes, because our z strictly represents the height. Our z equals f of xy in this is giving us the height, okay? When we find volume with variable density, we're going to need to use a triple integral. So we're not to that yet, okay? You got a question? It's a surface, okay? Specifically, it's a surface over a region. And then combining the two makes it a solid once we add another integral. Okay? All right, so now we're going to kind of go back through a different little checklist of things that you understand. If we had the integral from a to b of dx, that would find us the okay, you would never do it that way, but that's how you would find the length of the x-axis. Do you agree? It basically would become b minus a. We're using calculus to do subtraction. Okay? You agree with that, though? All right, so okay, so now if we change that to the integral from a to b ds, well, that's the same thing as the integral from a to b of the square root of 1 plus f prime of x squared dx. Do you remember what that gives us? That's arc length, okay? Can I re-explain to you why that is, what it is? Because I only learned it last bell. All right, so y equals f of x. If we wanted to know, if we took a string from x equals a to x equals b, and we followed the curve, how long would that string be? What we would want to do is divide it up into different little pieces of s. I didn't choose s. Somebody else chose s, so I just went with what they chose. You follow that? So that is a simple explanation for that. Now let's figure out how the heck do we get from here to there. Is anyone else wondering that? Okay, well, it just comes down to Pythag. So if we said, obviously using calculus, what we're going to do is add up all these little hypotenuses, right? And as those hypotenuses get really, really, really small, then our estimation starts to approach the arc length. And as we turn them into Riemann sums and they approach infinity, then it gives us our actual exact arc length. Right? Okay, so we call this dx and dy little differentials, little change in x and a little change in y. So what is each little ds? Excellent. Okay, it's just that. Well, look, up here, we had an integral with respect to x. So we had an integral, we had a dx. We had an integral, we had a ds. Here, we don't have anything with respect to. So actually, they get from here to here by doing a little trick. Okay? Well, they say this is the same thing as the integral from a to b of they basically multiplied this one by dx squared over dx squared. Okay? And they multiplied this one by dx squared over dx squared. Sorry. It's kind of like that. I'm missing that little parentheses. And then what you get is the integral from A to B of, this is a 1. What's dy over dx? Plus f prime of x squared, and then take that dx squared, and now we can integrate it. So that's where that came from. I never really understood that in the first place, but now I do. Okay? So once again, that was for what? Arc length. Got it? Okay, well after that, we learned our first double integral. And that was, what I'm trying to parallel this. What do they call that? I guess the area of planar region. Okay, so just like it was unnecessary for us to think about using calculus to do the subtraction, but we could do it, this one, now we kind of go back to, okay, well, this was unnecessary, but we used it to kind of understand. So here's what we're going to do today. The double integral over the region of 1 plus the partial derivative with respect to x of a z function squared, I didn't need this, sorry, plus the partial derivative with respect to y of a z function squared. And now this is a dA because we're integrating it over a region. This gives us the surface area. And then I'll put this in parentheses, but it's important to understand it. Over a region. And that's why we're referring to that as the area of the cap. Okay? So this is our new formula today, and that's going to be the end of the video. The integrals are going to be nasty, so you're going to be doing almost all of these in your calculator. Occasionally they might set up well. But so that's why we don't have a ton of work assigned for this chapter. I just need you to kind of understand that. If you really want to follow the rigorous proof, then you should read very carefully page 971 a couple times. You'll see that what we're approximating here is we're saying that if I wanted to find the area of this little region here, I would say I would use a tangent plane at this point. So imagine a blue tangent plane. And if I found the area of that tangent plane, it would very similarly approximate the area of that piece right there. And as we took infinitely many more tangent planes and added them up, we could treat them like mosaics, if you will. And that would give us eventually a very good estimate, and then eventually, using Riemann sums, an exact representation for the surface area. So if you really want to understand the rigorous proof, that's what goes into it. It uses cross products, and it's on page 971. Otherwise, you can get to work. Boom!